This video covers the first 4 sections of Chapter 7 on alkenes. We'll be talking about the preparation and use of alkenes, how to calculate the degree of unsaturation, naming alkenes, and cis-trans isomerism. And here's a cute little pumpkin dancer to liven your spirits. Because hey, it is October, so there's Halloween and there's pumpkin carving that you can look forward to this month. An alkene is just a hydrocarbon that contains a carbon-carbon double bond. Sometimes it's called an olefin. And here are some examples. So beta-carotene has a lot of double bonds. Ethylene and propylene are the least complex alkenes, but they're very important industrially because they lead to a variety of useful chemicals. So ethylene, for example, the 2-carbon alkene, can lead to all of these different organic compounds. Industrially, ethylene, propylene, and butane are synthesized by steam cracking of light alkanes. So notice the arrows are the fishhook arrows here, so this is a radical process. So under very, very extreme heat, 900 degrees Celsius, you can symmetrically cleave that carbon-carbon bond to produce 2 radicals, which then can lose a hydrogen to form ethylene. And then hydrogen gas is also formed as a byproduct. Alkenes have fewer hydrogens than alkanes with the same number of carbons, and therefore are referred to as unsaturated. So if we compare ethylene here to ethane, ethylene would be unsaturated, ethane would be saturated. We will want to calculate what's called the degree of unsaturation, which tells us the number of multiple bonds or rings present in a molecule. And the formula for a saturated compound is CnH2n plus 2, where N is the number of carbons. Each ring or multiple bond replaces 2 hydrogens. For example, the formula C6H14 is a saturated C6 alkane. However, if we looked at C6H10, that would be unsaturated, and the degree of unsaturation would be 2. And here are the possibilities for the formula C6H10. It could have 2 double bonds, it could have 1 triple bond because each pi bond is worth 1 degree of unsaturation. It could have 2 rings because 1 degree of unsaturation is either a pi bond or a ring, or it could have a ring and a double bond. So this talk of unsaturation and saturation may make you think of butter. And maybe you are feeling curious, like these cute little puppies here. Well, when we talk about unsaturated and saturated fats, we are indeed talking about how many double bonds they have. So saturated fats have no carbon-carbon double bonds in them. Monounsaturated fats have 1 double bond, and polyunsaturated fats have multiple double bonds. To calculate the degree of unsaturation, we simply use this equation. So yes, we do have to do a little bit of math here. In this equation, X is any halogen, N is the number of nitrogens. Other elements that aren't listed, we just ignore. And 1 degree of unsaturation is equal to 1 pi bond, or 1 ring. So a triple bond, for example, has 2 pi bonds, so that would have 2 degrees of unsaturation. So let's try an example. For the 3 formulas listed here, can you first calculate the degree of unsaturation and then draw 3 possible structures for each? So pause the video and try this yourself, and you can put your answers for the degrees of unsaturation in the chat. Okay, let's try the first problem. The formula was C4H8, and the first thing I want to do is calculate that degree of unsaturation. So it's 2 times the number of carbons, which is 4, plus 2. There are no nitrogens and there are no halogens, so I can ignore those, minus the number of hydrogens, which is 8 divided by 2. So 2 times 4 is 8, plus 2 is 10, minus 8 is 2, divided by 2 is 1. So this has 1 degree of unsaturation. So what are the possibilities? It could be cyclobutane, a 4-membered ring, where the ring is the 1 degree of unsaturation. You could have an alkene, where the double bond is between the first 2 carbons. You could have it where it's between the second and third carbons. You could also have an alkene that looks like this. And you could have a cyclopropane ring with a methyl hanging off. So those are the possible compounds you could have with this formula. Okay, let's do the next one with the formula C4H6. First, I calculate the degree of unsaturation, which is 2 times the number of carbons plus 2. There are no nitrogens or halogens, so I can ignore that. Subtract the number of hydrogens and divide all of that by 2. So I get 2 times 4 is 8, plus 2 is 10, minus 6 is 4, divided by 2 is 2. So this has 2 degrees of unsaturation. That means I could have 2 rings, 2 pi bonds, or a ring and a pi bond. So what are the possible structures here? I could have an alkyne, so that adds up to C4H6. I could place the triple bond in between different carbons to look like this. So those are my 2 varieties of alkyne I could have. I could have a ring and a double bond like this. Alternatively, I could have the cyclopropane with a double bond in it and the methyl. And then I could place the methyl on different carbons. So like this. I could also have the double bond external to the cyclopropane. And then finally, I could have something called an allene, which is 2 double bonds side by side. So that would be one possibility. Or I could have the 2 double bonds not directly side by side. To give me that diene structure. A diene just equals, it has something that has 2 double bonds. The final example, C3H4, when we do the formula here, we get 2 times the number of carbons plus 2, there are no nitrogens or halogens, minus 4 divided by 2 equals 2. So that also has 2 degrees of unsaturation. So we could achieve that by having an alkyne, we could have another allene where the double bonds are directly next to each other. They're not interspersed with a single bond. Or we could have a cyclopropene where you have the 3-membered ring with the double bond in it. Next, you want to learn how to name alkenes. So we're going to name the parent hydrocarbon, and we're going to change the ending from ANE to ENE. ENE because it's an alkene. So for this compound, it's 5 carbons, 1, 2, 3, 4, 5, and the longest parent chain. And so pentane becomes pentene. And then similarly, the longest chain here has 6 carbons, and it has a double bond, so the name goes from hexane to hexene. Now when you're figuring out the longest chain, when you have an alkene, you want the longest chain that contains the double bond. That's very important. It must contain the double bond. Next, you want to number the carbons in the chain so that the double bonded carbons have the lowest possible number. So you're going to start from the side that gives the first carbon of the double bond the lowest number. So in this example, we'd start over here on the right with 1. And in the example on the right here, actually it doesn't matter which side you start on, you get the same numbering. So in that case, we revert to our rule that we start on the side with the branching at the earliest possible number. So we start numbering from the left here, because that puts this branch, the methyl, at the lower number 2 than if we had started numbering from the right-hand side. Then you want to write out the full name, and you want to indicate the carbon number that the double bond starts on. So this becomes 2-hexene. This becomes 2-methyl-3-hexene because the double bond starts at 3 and there's a substituent at carbon 2. This becomes 2-ethyl-1-pentene because the double bond starts at carbon 1. This would be 2-methyl-1,3-butadiene. So notice here that we've got 2 double bonds in the molecule, so we're going to use the prefix di in front of the ene suffix. So this becomes a diene. Here, when we have a cyclic structure, we still use the cyclo prefix like we saw previously, but we just changed that suffix to ene. So this becomes 1-methyl-cyclohexene. This would be 1,4-cyclohexadiene. And this would be 1,5-dimethyl-cyclopentene. With this example, you may be wondering why this was carbon 1 and not this carbon. If you have a choice, you always want to make the carbon 1 of the double bond in the ring the one that has a substituent attached to it. And then when you number, you have to number through the double bond. So you can't number this way, you have to number proceeding through the double bond. A lot of these alkenes have common names. For example, the systematic name of ethene is commonly instead referred to as ethylene. Propene is commonly referred to as propylene. 2-methylpropene is commonly referred to as isobutylene. And 2-methyl-1,3-butadiene is commonly referred to as isoprene. Now try giving the IUPAC names for these compounds. So pause the video, try this on your own, and then put your answers in the chat. So here is the solution. The longest chain containing the double bond would be a 5-carbon chain. 1, 2, 3, 4, 5. We want to number so that we give the carbon of the double bond the lowest possible number, so that will be numbering from the left. There are 3 methyl groups at carbons 3 and 4, so we have to use the prefix tri before methyl, and then we have to indicate which carbons those methyls are on. So then the full name becomes 3,4,4-trimethyl-1-pentene. In the next example, the longest chain that contains the double bond is a 6-carbon chain, so this is going to be hexene. The methyl group is attached to carbon 3. And the reason we start numbering from the right, because right or left you get to the same number for the double bond, is that you get the substituent at the lower number if you start from the right. So then the methyl group's attached to carbon 3, and then this entire molecule becomes 3-methyl-3-hexene. Now again, pause the video and try this on your own and put your answers in the chat. So here for problem A is 1,2-dimethyl-cyclohexene, so it's a 6-membered ring, which would be cyclohexane, but there's a double bond, so that becomes cyclohexene. And then the one below the answer is cut off here is 4,4-dimethyl-cycloheptene. So it's a 7-membered ring, so cycloheptane, but it has a double bond, so cycloheptane becomes cycloheptene, ene. And then you would number in the direction starting at one of the carbon-carbon double bond carbons, such that the substituents arrive at the lowest possible number. So that would be the numbering shown here. If instead I had numbered in the other direction, 1, 2, 3, 4, 5, 6, those 2 methyls would have been located at a higher number. The final topic is cis-trans isomerism in alkenes. So when you have a pi bond, rotation around that carbon-carbon double bond is prohibited. And if you actually rotated that, then you would break the pi bond. As a result, we get cis and trans isomerism. And compounds with substituents on the same side of the double bond are called cis, and those with substituents on the opposite side are called trans. and this will occur whenever both double bonded carbons are attached to two different groups. So here are pictures of cis and trans 2-butene. So here we can think about the double bond being cut in half here, and the methyls are on the same side of the double bond. Here, if we cut this in half like this, we see the methyls are on opposite sides. Sometimes people get confused and they want to cut the double bond like this, but that would actually just break the pi bond and you'd just be looking at things attached to the same carbon. You wouldn't be looking at which side of the double bond substituents are on. Now, for there to be cis-trans isomerism, the end groups need to differ. So, for example, if you have molecules that look like this, these are actually identical because you could just take this and flip it over to make it look just like that. So the groups here need to be different from each other. They can't be identical groups. So notice here, these groups are different from each other, and these groups are different from each other. So here, these compounds can have cis-trans isomers. So is this alkene cis or trans? And it may help to put in the hydrogens. So what do you think? Put your response in the chat. And now you have finished the video, and these doggies are congratulating you. I'll see you in class.